going to review questions or some students have had PDEs and some haven't. Yes.
So I'll talk to your part of
Okay.
That's all.
There's just two per semester? Okay.
Because next is the time we can think we would like to have something like this done in the spring instead of have everything for the fall.
Okay.
Because right now we are really in this so many things just unbelievable. So each you get it to and then imagine all the people and also it's not much time, only at the beginning of the semester.
I think there were some part of it doesn't exactly get
Fall.
Yeah.
Never happens.
That was fun. Okay.
For 1 year.
Well,
I
yeah.
think
This is your first year as the chair, right?
I don't know what happened. I asked the question. I said, well, what's this? But anyway, we have this many so we can get it. But I know all those people are so busy.
Yeah.
And the committee, so on the committee, so these members all I think this stress.
Yeah. A lot of people.
So many meetings already. This semester, this is still at the beginning of the semester. We already have 2 meetings, and the third meeting is this Friday.
Okay.
And then after.
In the first 2 weeks.
Yes, yes. So we have to get it together for the faculty.
Yeah.
And then after that, we will be able to. For October, November, probably not much.
Okay. Let's get past that to the high
Yeah,
level.
but October, not, well, still, we need to do everything. October is no meeting, but work.
Yeah.
This is everything will work possible. But we'll see.
Yeah.
Last year, I think we went to total of 5. 5.
12.
So it's double.
So to start, just a reminder, today we're going through a journal article, the very first journal article we're going to go through in the semester. So I'll continue on with Module 2 lecture until about 10:45, and then we'll switch gears and talk about that paper. So continuing on with Module 2 lecture, this is where we were at the end of Tuesday. And so we were, let's say, to kind of give a recap on Tuesday, we were starting to get into partial differential equations. We went through some simple ones in 1D, and now we're getting into ones a little bit more complicated in 1D. This is the case where we have a moving heat source. So you'll actually see a direct application of this in the journal article that we're going to go through at the end of today's class. But then you can start to draw analogs to this in some processes in additive manufacturing, where you have some sort of heat source that's scanning along some sort of surface. Okay, so just to recap from where we were, we had basically an infinite rod, so this extends in both positive and negative infinity. We have 0 initial conditions, and then we have this heat source denoted by a Dirac delta function that is at position Vt, where V is a constant velocity. So just imagine, in the example we're going to give for the paper we have later today, it's going to be arc welding process, where we have basically an infinite rod moving along, and then we're heating at one end. But also projecting this onto additive manufacturing, this would be a laser, say, scanning across the surface at a constant velocity. And we're going to look at the temperature profiles that develop from this type of non-homogeneous term into our system. So we started just like with the other problems. We started out with the diffusion equation, which is given here, or diffusion problem in 1D. And we said that if we want to look at this, we're going to look at a change in coordinates. And so instead of looking at this global coordinate frame of x, we're actually going to translate this to be this zeta frame, which is a frame that moves along with this heat source. So just imagine you have a camera, and that camera's following this heat source as it moves, in this case, to the right, along the positive x direction. So that's going to be what we're looking at. To do this, we have to look at multivariable calculus, and especially the chain rule multivariable calculus. So the first thing we did, the last thing we did before we adjourned on Tuesday is we looked at, with this change in coordinates, what is the partial of u with respect to t? All right, so we looked at, this was just a dummy example to give a review of the chain rule of multivariable calculus. And then we looked at how this directly applies to the partial of u with respect to t, when now we have a substitution where we have a change in coordinate in x. Right? So what was du dt, when we have this change in coordinate, now becomes du d zeta times d zeta dt. Right? We said that d zeta dt, by definition, is going to be negative v. And this is coming directly from our definition of zeta when we did this change in coordinate. Right? Take the partial of zeta with respect to t, we get negative v. Right, and then we have partial of u with respect to t again. Okay, so again, what was partial u with respect to t now becomes partial u with respect to zeta times negative v plus partial u with respect to t. Okay, any questions about that? Okay. So if we look at our partial differential equation again, so this covers this term right here. We now need to handle this term, the partial of u with respect the second partial of u with respect to x. So this one's considerably easier. So if I look at this, it's going to be partial u. U is a function of zeta plus vt. Partial x squared. Sorry, I'm skipping steps here. Let's do this just for the first one. Okay, so the first time we do this, it's just going to be partial of u with respect to zeta, partial of zeta with respect to x. Okay, so partial of zeta with respect to x, if we go back to our definition, right, partial of zeta with respect to x is going to be equal to 1. So then we're going to get partial of u, partial zeta, times 1. Okay, so this one's easier than the other one, right? So if we take what was du dx, or partial u partial x, now becomes just partial u partial zeta. If we were to do this again, we're going to get exactly the same thing. And just using shorthand for the partial, this would be give us u sub zeta zeta, right, for this part. Okay, so if we now put this all together, we get our new partial differential equation. So this is 0. This is now, if we look at our boundaries, or sort of our domain, we have now this domain. Zeta goes from negative infinity to infinity. T is still a domain greater than 0. And now we have a change in our initial conditions, which is not much of a change at all because we had 0 initial conditions to begin with. For this particular problem, it remains to be equal to 0. And then by the problem statement, we're looking at this as steady state. And so by steady state, that means is that the partial of u with respect to t is equal to 0. We're talking about steady state analysis. So we'll be looking as this camera moves along, and we're going to look at the steady state response as also. Well, basically, the camera is moving along because we're changing a frame of reference. The heat source is moving along at the same speed, and we're looking at the steady state response of temperature in this material. All right, so that means that our new differential equation here, I'm just going to subtract out, subtract out the v here. So I'm going to get then my new differential equation is this here. Domain is again the same. And the other thing to note here is that this is an ODE. Okay, so what started out as a PDE with this change of coordinates, and also assuming that we're looking at steady state, what was a PDE now became an ODE. So this should be much easier to solve. Okay. All right, so the way in which we're going to solve this is we're basically going to find a Green's function for this. And so that combine the Green's function, in other words, is just the impulse response of the system. And we're going to take a look at what that is. Okay, so we already have a direct delta function as a non-homogeneous term, so we're already looking at the impulse response. But if we're saying we're looking for a Green's function here, we're looking for, before, from previous lectures, we called the Green's function as, I don't know why that's not going away. Some sort of source function or Green's function. Okay, also known as the solution to the impulse response. So if this is our solution, then we can just plug this in for what we want to solve for, right? So we're trying to solve for temperature, U, here. So if this is our solution, if we just plug this in terms of having this integrating factor as a change of coordinates here, then we have S second partial with respect to zeta, zeta minus y, v over k, all right, first partial of s with respect to zeta, zeta minus y. All right. So now from this definition here, we can start to look at the solution to this, right? So if we want to solve this differential equation, especially with impulse response, we have to look at a few different scenarios. So the first one is we're going to say that zeta is not equal to y. Okay, so for zeta not equal to y, we know that this direct delta function has this form. Say we have some sort of dummy variable x. The direct delta function is this infinitely tall spike centered around x equals 0 and infinitesimal width. So if we look at zeta not equal to y, that means the argument here is not equal to 0. So that means that this right-hand side is going to be equal to 0. Right? So for zeta not equal to y, we get this equation. Equal to 0. Okay, so this is an ODE, which is something that we reviewed at the very first part of this module. Right? So the solution, just kind of skipping some details, the solution to this ODE is that S of zeta minus y is equal to C1 e to the negative v over k zeta minus y plus C2. That's the standard solution to ODE. All right, so we said that zeta is not equal to y, but we didn't say which one is larger. So it's instructive to look at C, which one is going to be larger. And to do that, we're going to have to apply the boundary conditions for this problem. So anytime you have an infinite domain, one of the assumptions for the boundary conditions is that the derivative of that solution with respect to the spatial coordinate is equal to 0, or that the slope at infinity is equal to 0. Okay, so we can look at this. We can look at what would be then the evaluation of this boundary condition. So here is our function for our Green's function, or source function. If we look at what is the derivative of this function with respect to zeta, so we have a zeta in the exponent here. We get S zeta, zeta minus y, this function right here. If we say, let's look at the first condition we're going to look at is zeta less than y, and apply boundary conditions. Okay, so if we have zeta is less than y, it's instructive to look at the case of just plug in zeta is equal to negative infinity. Okay, so if we plug in zeta is equal to negative infinity, what I'm going to get is essentially negative infinity minus some number that's smaller than infinity. So we can essentially say that this term here is negative infinity. We have a negative, basically a negative 1 in front of this term. So this is going to be e to a positive number, right? Essentially e to positive infinity, right? Which blows up to infinity. Right? So what this tells us from this evaluation, so if I look at this, this means this whole term blows up to positive infinity. What this tells us is that C1 is equal to 0 for this condition here. Okay. It says nothing about C2 yet. We'll work on C2 in a little bit, but this is just saying that for the conditions of zeta less than y, we know that our solution is just equal to C2. Okay, we'll get into a solution for C2 in a second, but we just know it's C1 has to be equal to 0. Okay, any questions about that idea? Okay, so other case. Zeta greater than y. So we're essentially saying test at zeta is equal to infinity. So I'm just going to delete this here. So same argument as before. The partial of zeta with respect to, partial of s with respect to zeta gives us this equation here. If we have zeta is equal to infinity, this is infinity here times a -1. That's negative infinity. We know that this converges to 0, right? So the main realization here is that C1 in this domain is not equal to 0. Okay. The two-part solution we get is that our solution to this partial differential equation is equal to C2 for zeta less than y, C1 e to the negative v over k, zeta minus y for zeta greater than y. Okay. Then the next question is what happens directly at zeta is equal to y. Right, so what we get here is that C2 is equal to C1 e to the negative v over k zeta minus y. All right, so zeta equals y. This is e to the 0, which is equal to 1, right? So we get that C1 has to be equal to C2 for this to be true, right? For this to have continuity in our solution. Okay. Also at this situation, we have to look at, if we go back to our original differential equation, we can start to understand, we still don't know what C1 and C2 are yet, but we can go back to our original differential equation to figure out what this is. Okay, I ran myself out of room in this PowerPoint slide, so I need to add a slide to this. Okay, so our original differential equation was this. If I integrate both sides over the infinitesimal width of my Dirac delta function, what I get is limit epsilon goes to 0. These terms. Okay. So this may be some review for you. You'd have to go back to your systems classes in undergrad or go back to differential equations classes from undergrad. But a fundamental property of the direct delta function is that the integral of this function, even if this is infinitesimally large, from negative epsilon to epsilon is equal to 1. Okay. So we know that this term here, this whole integral is going to be equal to 1. All right, so the right-hand side is going to be equal to negative qk. Left-hand side, we can apply some basic principles of calculus. So we know that the integral with respect to d zeta, when we have that a derivative with respect to zeta, here this happens to be the second derivative here, but basically this is just the same as looking at basically taking one of these derivatives with respect to 0, right? So just like the fundamental theorem of calculus. So if I look at how I evaluate this, I now say limit epsilon going to 0 to the right. This then becomes, this term right here becomes s epsilon evaluated at positive epsilon, or sorry, s zeta evaluated at positive epsilon minus s zeta evaluated at negative epsilon, plus then bk s evaluated at epsilon minus s evaluated at negative epsilon. Okay. So going through these different terms here. So we know from the work we did in the previous slides here, right, we already evaluated this for basically the partial of s with respect to zeta, and now we should evaluate this at epsilon, which is essentially 0. Right? So this is still limit epsilon going to 0, negative v k. This is C1. Right here. This one, right? So we said that for any time in which the argument of this function is less than 0, that the function is just plain C2, right? So the function C2, taking a partial of C2 with respect to zeta is going to be equal to 0. That's just a flat function, right? So we know that this side here is equal to 0. We now have plus bk. Our positive function was C1 e to the negative v over k zeta. Our negative function was minus C2, all equal to negative Q over K. Okay, so 0 doesn't matter. We have a minus V over K times this term, plus V over K times this term. These two are going to cancel out. And we get ultimately that C2 is equal to Q over K. Okay, so we're able to find then our unknown. We know that also that C2 is equal to C1 from the previous slide as well. Okay, so this completely defines our solution to our differential equation. So just as a recap, our differential equation is u of zeta is equivalent to saying our Green's function for this S of zeta is equal to Q over V for zeta less than 0, and it's equal to Q over V e to the negative Vk zeta for zeta greater than 0. Right, and for zeta equals 0, either one of these work. They're going to give you exactly the same solution. All right, so if we were to plot this, here is what we get. So this is the zeta less than 1, or less than 0, I mean. Flat line, this is just held at that temperature. For zeta greater than 1, this is then this decaying function. I think you'll see in the paper we're going to go through the implications of this. But what this basically is saying, if we go back to the original problem statement, keep in mind what we did is we instituted a change in coordinates. So that means that we have essentially a camera following along this heat source as it travels along this line. That means is that anything behind this heat source has the same temperature. Anything in front of this heat source has a decaying profile as we go along, which makes some sense, right? Especially the positive zetas. You would expect that something really far in front of this moving heat source that hasn't been hit by it yet to be at the ambient temperature, right? Not to be elevated. Once that heat source passes, it doesn't actually dissipate. For this case example, it stays at an elevated temperature. But then, so just going back, trying to map the problem to this. All right, this is behind the heat source after the heat source passes. This is all in front of the heat source. The other thing to keep in mind is as your velocity gets to be slower, so this is for constant Q. As your velocity becomes slower, the heat taken up by the rod becomes higher, and therefore the temperature is higher, which makes sense, right? All right, so if you have constant heat in terms of heat rate, and you're moving along the slower, it's going to heat up the area for a longer period of time. So this is increased rod temperature as their velocity slows down. It also allows heat to diffuse forward a farther distance as well. Right? Whereas if you're moving really, really fast, the area of the rod doesn't heat up as fast because the amount of energy per unit of time going into that area is lower. And also, there's a faster decay in terms of how heat propagates in the forward direction on this part. And we'll directly see the implications of this for the paper we're going to talk about. And we'll see this when we get to powder bed fusion processes and other additive manufacturing processes as well. Any questions about this problem? Yes?
Translating this, like, is it typically a higher velocity or lower velocity when you actually apply this? Is it because of the material you're trying to?
Yeah, so it's very dependent on the material. There's actually it's a fairly sensitive, well, so when in a, say, laser powder bed fusion process, the laser is scanning somewhere around 1 meter per second in the process, in that order. There's a fairly small processing window where you either heat up the material too much, so you can imagine if you're moving too slow and you're dumping too much energy into a certain area, it's going to get too hot and you're going to have problems there. And there's also, if you're moving too fast, you have this problem where you're not putting enough heat into the process to actually melt it, right? So as my velocity goes up, my temperature in that region goes down. So if you're going so fast that you're actually not welding enough of material in that region, you're going to have problems with what's called lack of fusion defects. So this right here, I'm not showing the change or how this temperature response changes with Q, because that's a very linear relationship if we go back to the equation, right? So the height here is linear in Q. It's not so nice and clean when you look at velocity, right? So velocity in terms of the decay rate is in the exponential, so that's a little bit more difficult thing to plot, so I plotted that one. But basically your two knobs are going to be your power of your laser, which is your Q, and then also the velocity at which you scan your laser. So they're the two main things you can control. There are other things you can control, but those are the main things that basically technicians and engineers in additive manufacturing look into. All right, so this is the 1D problem. we're doing additive manufacturing, we're building three-dimensional parts, right? So we have to get into higher spatial dimensions when we talk about PDEs. Okay, so here's the diffusion equation for higher spatial order. So looks very similar. You still have this term's the same. This term becomes a little bit more complicated here. So instead of having partial of u with respect to a partial squared of u with respect to x squared, now we have in the y and z direction, and then we can have non-homogeneous terms x, y, z, and t all included here. Our domain, if we're talking about the infinite domain, which is what we were talking about for the previous problem, you can see the domains listed here going from negative infinity to positive infinity for each. And then also we can specify initial conditions for the temperature in x, y, z as well. Some notation. Oftentimes we'll do shorthand x, basically the boldface x to be the vector that includes the triad x, y, z. This is called the Laplacian here. So we take the Laplacian of the temperature, that's du dx, du dy, du dz. And then, especially when we're talking about the diffusion equation, we're looking at Laplacian dot Laplacian of u, or oftentimes you'll see Laplacian squared. Some textbooks, they'll define Laplacian squared as delta for shorthand. But we'll use Laplacian squared. That's because basically some of the books that are useful, or some of the journal articles that are useful for additive manufacturing tend to use this notation. So we'll try and stay consistent with that, and that becomes now basically this term right here. So the shorthand for this would be du dt minus k Laplacian squared. U is equal to that or non-homogeneous term. Okay, so just as before, the solution has to satisfy the PDE, initial conditions and boundary conditions, and then some of these ideas that we talked about in one spatial dimension, we're going to use these in 3D or 2D and 3D for additive manufacturing processes as well. And I think they'll become a little more clear. I'm going to go through two examples in 3 dimensions that I think will help solidify this idea. Okay. Boundary conditions for heat transfer. This is a slide that we have seen before already. I showed a simplified version of this. Already, this is just basically a repeat of that. I don't think there's anything new, but I just want to note that actually there's nothing new here that I haven't shown before. But this is basically you have to consider boundary conditions, and we're going to start with this example here. So this example is very similar to the one we just looked at, but there's going to be some differences, especially the form of the Green's function. We're not going to go and derive, the previous example we derived the Green's function. Here we're not going to derive it, we're actually going to take it from a table, or basically the previous work, but you'll see how this can be applied. So before we consider the infinite rod, no infinite rod exists. This is probably even more abstract. We're going to consider an infinite body, which I'm denoting by this cloud. So picture you have this infinitely large block of metal, and somehow you're able to put a heat source somewhere in the middle of that block of metal. So probably not too realistic an example, but it's going to be instructive for when we get to a more realistic example than this. So anyhow, infinite block of metal in all directions. That means our domain goes negative infinity to infinity in the x, y, and z direction. This heat source, again, is moving. So it's moving along the x direction with the velocity vt, and it's moving along, and it's not moving in the y or z direction at all. Okay, so here's, if you look at our coordinate axis, right, this heat source is moving along the x direction. And we're trying to understand that what is the temperature inside this block of material. Okay, so again, we're going to start from the diffusion equation. All right, and this is the proper formulation for the diffusion equation. Our domain, oftentimes we'll denote this just by d colon, is in shorthand from negative infinity to infinity. The vector x, remember the vector x is the triad of x, y, z, are bounded by negative infinity to infinity. Initial conditions, all equal to 0. And here's our definition. Here. Okay, so just like the previous problem, to do this, we're going to consider a moving coordinate frame. Right, so we're going to do a change in coordinates. Zeta is equal to x minus vt. Okay, so before, I think it was maybe a little easier to think of like this infinite rod, and you have now a camera that just follows along the laser source. Same idea here, but now you have an infinite volume. You're still just going in the x direction at a constant velocity with this camera, vt following along this laser source, and we want to know what is the temperature profile around this laser source here. Okay, starting again, very similar to what we had before, we're looking at what is now ut when we did this change in coordinate. So ut, where u is now a function of zeta plus bt, y, zt, All right, so we do the full chain rule for this equation. We get this long expression. So going through this, one thing to keep in mind, for these terms in which now we did not institute the change in coordinates, y is not a function of t, z is not a function of t, right? So we never defined them as functions of t. So we did define zeta as a function of t by our change in coordinates, right? So both of these terms go to 0. Those do not influence this. This is exactly the same for the 1D case, and so this is exactly the same for the 1D case. So I get ut negative v du d zeta plus du dt for this term. Just like the 1D case, when we looked at partial of u with respect to x and double partial of u with respect to x, we just got this relationship. Same idea here. All right, so this change in coordinates just changes the subscript on this second partial, and that's going to have no effect when we look at partial of u with respect to y, partial of u with respect to z. Okay, so our new PDE is going to be this. We have to redefine what we mean by the Laplacian squared. So before we were in the coordinates of x, now we're going to be in the coordinates of zeta. Our triad of spatial variables is going to be now zeta, y, z. And then our domain is still infinite in all directions. So domain infinity in every direction. All right. The derivation of the Green's function for this is, let's just say it's not easy. So we're going to actually use basically from known Green's functions, and basically from tables of known Green's functions for this. The notes actually have, the handwritten notes are going to have a demonstration that this is indeed the Green's function for this type of partial differential equation. But I'll cut to the chase on this, is that the Green's function for this, because the main part of this example is not this exact solution, it's the next one I'm going to show. But the Green's function for this is this equation. Okay, so let's talk about this a little bit, because I think there's some interesting features of this. Okay, so if we look at this Green's function, this is talking about what is the Green's function is a solution to the impulse response, right? Our impulse, and so if we want to know, and we have a PDE in which we have the non-homogeneous term is the impulse function, right? So if we know the Green's function, we know then the solution to this PDE. So if we want to look actually what's u, this is a scaled impulse response, so this u is just going to be that the scale times our Green's function. So let me make sure that's not confused as a delta, that's s. Okay. So some interesting things to think about here. So for those of you who have seen multivariable Gaussian functions before, if we have just a single variable Gaussian function, we're usually talking about, say, e to the negative p squared. That's a function that looks like this, right? If I have e to the negative, say, r squared, where r is the distance from the origin, then we have functions that look like this. These are two-dimensional Gaussians, and then we have to project this into 3D if we want to look at what is a three-dimensional Gaussian, right? So which is exactly what we have here. So these are essentially spheres of level sets in terms of temperature here. So the main thing I want to point out that this is symmetric. This term here is symmetric about the origin, essentially in all directions. This term is also symmetric about the origin in all directions as well in the denominator, right? Because they're equally balanced in zeta, y, and z. Where we get a asymmetry is because of this term right here. Okay, we'll see how this manifests itself in a second. Okay, so these are, it's impossible for me to plot this in all three dimensions, so we're just looking at 2D projections here. So these colors here are basically temperature values. Think of these as temperature values for different velocities at which we're moving along. So very similar to the 1D case. If we're going slow, this is, I didn't put units on this, so it's kind of tough to imagine, but look, if you go slow, then the hot temperatures project farther into the front because there's more time for the heat to diffuse forward in this direction for positive zeta. If we're going fast, you see that the temperature almost purely trails here. So it does not heat up in advance of this heat source much at all, but then all the heat is behind it as it moves forward. And that's where we get this asymmetry here. So going back, we have this asymmetry. This is a function of velocity, and it's also a function of zeta. So it's completely symmetric in the y and z axes. It's asymmetric in the zeta axis, and the larger v is, the larger the asymmetry is in that temperature response. Okay, so as we get in 3 dimensions, it's going to always be a little bit more difficult for me to plot and demonstrate, but this is a tool we can use. This is using, I forget all the code for this is on Carmen. I'm forgetting the exact name of the MATLAB plot that gives you these contour plots here, but you can use MATLAB to create contour plots of any, in this case, 3-dimensional function. Well, we had to do a 2-dimensional function here. But the main thing I wanted to point out is this is what, as we get into additive manufacturing processes, this is the type of temperature profiles we would expect for slow velocities. This is more what a fast velocity temperature profile is going to look like here. All the high temperature areas are trailing the laser spot. Okay. We don't have time to get to this example. This is actually more physically relevant for additive manufacturing. This is in the half plane. We'll actually talk, I could talk to you about this when we get to the journal article that we're going to go through, because this exact solution is given in that journal article. This is the half plane. This is much more relevant to something we actually see in a manufacturing process. This would be something that is never exactly true, but it can be approximated. We're saying that the domain goes infinitely in the x and y directions, and then we're scanning a heat source along the top of some sort of surface of a really thick plate of material, right? So this is the infinite half plane here, where now the domain in z goes from negative infinity to 0, and we'll go through this essentially in the journal article after we take a break. So let's take a 5-minute break, and then we'll get into the journal article discussion. We'll reconvene at 10:55. Yes. So if you get zeta is negative infinity, and the y is larger than that, that means that this term here is going to be a very, very small negative number, or whatever you want to call it, right? Then you have a coefficient negative 1 alpha. So that's e to the positive infinity. And so we know that the boundary conditions that either zeta is equal to negative infinity or positive infinity has to be that the derivative. Sorry, you're looking at the wrong one, actually. We should be looking at we should look at the partial s with respect to zeta. But the answer is still the same. Yeah. So if we do s, go back to this zeta. All right, so that's just going to basically be negative bk alpha, right? Yeah. Okay. So, and the theta goes away, right? Yeah. Okay. So then you have e to the positive infinity, which is infinity. So that means that c1 has to equal to 0.
Yeah. Yeah, I guess. It's an indeterminate form, e 0 times infinity, but yeah, I get what you're saying.
No, why is it 0 times? Oh, yeah.
It goes
Yes. But, yeah, but that's not a limit, though, right? So this is, the limit as this goes to 0. This is just what is C1. There's not
Savings loss of pi, let's say the infinity is saying negative infinity minus 1 quantity seems to want to be negative, negative, plus. Yeah, there's going to happen. There's not a mathematical solution that doesn't exist at all.
Yeah, does that make sense?
Yeah, and then for greater than infinity, we repeat the process.
Yeah.
And then we basically just have to say that because it's going to be now plus infinity, it's going to be negative plus infinity. So we can't really make any definitive statement about C1.
Just that it's not equal. It's allowed to not be 0.
Yeah. And in fact, it will have to be equal to negative C2 to bring the solution. All right, that makes sense. Thank you. Yes, you see all my name on the poster list and everything.
Did you actually go to the online site to register and say what you want to eat and all that stuff?
I thought that was taken care of because I have my name registered for it. Oh, I didn't realize you could. I didn't realize you could put the name on it before that.
But you received the emails asking you to register, right?
Yeah, but they said anyone who hasn't registered, register now. I thought it was registered because my name was on the poster list. Never mind that. I'm gonna do that.
So this is an interesting paper because it's so old. This is a 1946 paper that was assigned for this one. So you may, and I was curious. I looked up and wanted to know when were lasers invented, and that was 1960, right? So this was the interesting part about this is that this is the basic equation that's used to try and understand laser processes and additive manufacturing. If you want to get fairly simple solution for what the temperature profiles and start to understand some of these relationships between laser energy laser speed, material properties such as conductivity, specific heat, and what you'd expect the temperatures to be. So this was developed before lasers were ever even thought of, but this was developed for welding. So, anyhow, 1946, this is in the transactions in the ASME. For those of you who are to the point in the graduate career where you're now reading journal articles, and you may be looking at ASME Journal of Heat Transfer, ASME Journal of Dynamic Systems and Control, all these other things. This was before they actually started to separate them. They just had, these are the transactions of mechanical engineering. So basically everything that was related to mechanical engineering was thrown in this single journal called Transactions of the American Society of Mechanical Engineers. So this is quite old. So that's, I think, makes it somewhat amazing that they are able to do some of these things. But I'm going to just go through, and I think in terms of a model for when you present these, you can't present an entire journal article in 15 minutes. It's just not possible. So try and select a subset of that you think is either really interesting to you, or some subset of it that you think is really interesting for the class or applicable to the class. And that's what I tried to do here is looking at the cases that are 1D heat transfer, which directly apply to the problems we just looked at, and also 3D heat transfer, in particular, what's called the methods of reflection, which I was hoping to get to that problem before the clock hit 10:45, but I was unable to. But we can go through it here to look at. It's a fairly simple idea. So the first thing in terms of trying to understand this, what is arc welding? Has anyone welded anything before? You have? So 2 people. Was it arc welding or a different type of welding? Arc welding, okay. What?
Do the flux. Like someone holds like a flux for you and you.
Okay. Oh, so it was like a separate bar coming in and you were welding it to the side. Okay. So that's a little bit different than what this video is here. Let's see. Just going to go. Problems with volume and all these things. Still not good. Okay. So I'll kind of talk through what's happening here in terms of arc welding. This is an arc welder. Maybe you've seen this in people on construction sites doing this. But what's going on is you have a consumable electrode that's right here. Oops, it doesn't like me writing on videos apparently. So this electrode is decreasing in size. You can see it here in this cartoon. You have a current running from this electrode into this plate. So you actually create an electrical circuit through here. You get then arcing of basically ionized gas in between this consumable electrode and the piece. And so then this consumable electrode is continually melting. It's then basically putting molten metal on this workpiece, which is also being melted because that's so hot. And you see this pool of metal then forming where your welding is. So if you've ever looked at a weld, you'll notice that it almost looks like a bunch of like ellipses stacked on top of each other as you're going along. And that's because you get these wave patterns flowing molten metal up, and then it freezes in that kind of a regular pattern if someone's making a good weld. Have you welded a lot of things before?
Not that much.
Okay.
Out of car.
Oh, out of car? Okay. All right.
It's much harder than it looks.
Yeah, so here.
The piece of it's hard. You gotta have like fine control of distance between your workpiece and your.
Yeah, I hear it's, I've never done it myself. I hear it is much harder than it looks.
So much harder.
Yeah.
Make it look nice. It's really hard.
Okay, yeah, so, and then it's funny, as you talk to the professors who are welding engineering, and they're all scientists, right? And so the ones who think they have street cred, they brag that they can start a spark start a spark. Even though they're welding engineering, I don't think most of them can actually weld themselves. So, yeah, I hear it's very tough. I've never done it, but that's the main process. Here's a schematic. Oops. Of the main idea, I'm by no means an expert in welding, but this is just kind of give you a sense of what's going on, is that you electrically ground the workpiece that you want to arc weld. This is then the power source for this, and then this is connected to the electrode holder, and then this is the consumable electrode. So you're continually feeding a piece of metal that is designed to then become part of the weld here. Looking at what's happening here, you have your electrode, which is covered by basically the flux, which when this melts creates a gaseous shield to it. The reason for this is because if you didn't have this, you would have a pretty intense oxidation of the liquid metal, and that causes poor mechanical properties. So you would have the same exact problem in additive manufacturing processes, by the way, if we did not have some sort of gas surrounding it. So that's why a lot of additive, especially metal-based processes, are in inert environments. So they're either in basically mostly argon gas is the environment they're in, or some of them are actually under vacuum for this. So the solution for welding is they create this material outside that melts and then creates this gas shield out here to prevent oxygen from getting to the surface before it solidifies and creates oxidized surfaces. So in terms of what's basically going here is that we have current running through the high resistance arc stream, and this is what this paper is modeling essentially as a point source of energy. And the system heats both the workpiece and the consumable electrode. Electrode approximates an infinite rod. Workpiece approximates a semi-infinite plate. So they're saying that this plate here goes to infinity. Well, not in all the cases. They went through a few different scenarios with increasing complexity in terms of the solution to the differential equation. But some of them, they're assuming that this plate goes off to infinity in all directions to make their life easier in terms of solving that differential equation. And to get solutions where you can just look at the equation and try to understand how the different variables affect the time solution. Okay. All right, so the first problem here is they're looking at essentially temperature in this consumable electrode. Right, so you have a essentially heat source right at this junction here, and then they're looking at how is temperature propagating up this electrode as it's going in. Right, so ignoring the plate here, and the assumptions that they're using is that the electrode is long with respect to the diameter, quasi-stationary. That means that this electrode is moving at a constant velocity, which maybe if you're a really good welder, you want that. If you're a bad welder, maybe you don't have the ability to hold that true. No surface losses. They're saying that the heat coming from the sides here is going to be equal to 0. And then no Joule heating. And so maybe my naive understanding of Joule heating is I didn't understand this assumption one bit. So Joule heating is basically heating that comes from current running through an electrical resistance. And to me, this is exactly the definition of Joule heating in my mind. The way in which they did this, though, to eliminate the idea of not having Joule heating is that they said that this is a solidification temperature here. So this is whatever the solidification temperature of metal is here. So and then this is the hottest temperature is right here. So instead of assuming that there is some sort of heat source, they said that there is just a temperature gradient here, and there's no Joule heating. So that all the heat transfer is coming from the fact that you just have two different temperatures. So this assumption had made no sense to me at all, but these people are dead, so I can't go and argue with them. Okay, so we just went through this problem. This is exactly, I mean, these examples I pulled were actually derived from this paper because we'll see these come up over and over again in additive manufacturing. This is exactly the problem we just went with the 1D heat transfer. We just did with the 1D heat transfer here. Okay. So this was the solution that we had. The only difference here is that we assumed that the boundary conditions were that T naught is equal to 0, which is obviously in the case of arc welding would not be the case. We did the T naught is equal to 0 for just to make our solution simpler. But basically all this does is just change the background temperature everywhere. So before we just said that T is equal to this equation essentially. Now this becomes T is equal to this equation plus T naught. They also went through some other relationships here, and then they pulled some things from the welding community that I wasn't aware of, but is interesting and helpful to try and understand the papers. That they say that via this relationship that this is the current running through the electrode, that this is proportional to the velocity at which you travel. So this is now tying back to some of the plots we had before, where we said that as the velocity decreases, the temperature increases. As the velocity decreases, the temperature increases. And then they were able to show this directly in very old photographs. So it may be tough to see this. This is, I believe, 145 amps, and this is 240 amps here. Okay, so before I read this paper, if you were to ask me, where would you see more, this is what's called the heat affected zone. This is where the metal actually physically changes. Where would you expect to see a longer protruding heat affected zone? The case where you had 240 amps or 148 amps, I would have expected that to be 240 amps because you're basically having high current density. And so that's why I think equations like this are fairly instructive to try and explain this phenomenon, because what this is basically saying is that if you want a good weld bead, if you're having higher current, you have to be traveling faster. And that means that the heat affected zone is smaller. So the heat affected zone is, in kind of brief words, the heat affected zone is the region in which you get appreciable change in the microstructure of the metal that you're working. All right, so this is then going back to, this is probably going way back to some like intro to material science classes you may have taken, where you look at these phase diagrams for metals. This is the phase diagram for steel, which is what the material they're looking at here. And we'll go through this towards the middle of the class, but basically there's some very sharp transitions between different phases of metal as you go from different temperature levels. Okay, so what you see here is, even though the temperature profile you would expect this electrode to be somewhat smooth, you get a very sharp line where the metal changes characteristics once you cross over certain temperature zones. And so you see a very sharp band where the heat affected zone is and was not when they're doing this. And we'll see this in, say, powder bed fusion processes. Here's a simple example of them just putting a small bead of material on a surface. So this was a base piece of metal in this region, which is going to have the microstructure of the metal itself. And then they melt with a laser powder in this region, and they get this heat affected zone that goes into the metal where you have a change in microstructure. This would be the metal powder that was melted up top, but basically this is what we would call to be the heat affected zone of this bead. So some of these ideas that came from the welding community, this would be 1 year after World War II, a very long time ago, right, are going to be instructive and helpful for us when we get to additive manufacturing processes. Okay. The next thing I thought was interesting is they started to look at 3D heat transfer, and I think what I thought was the most interesting for this class is what they said butt welding in thick plates. So for those of you who have never heard of butt welding is you take two pieces of metal and then you put a weld along the seam to then basically turn two pieces of metal into one welded piece of metal here. So their assumptions is that they have no heat loss through the surface. And so what they're saying is that at this surface and in this surface, they have what's called the Newman boundary condition, which we talked about. And so that means if we look at what is the partial of U with respect to Z at the position of 0, that's equal to 0, and then the partial of U with respect to Z at what they're calling G, or actually negative G, that's the bottom of this. They're saying that's equal to 0 as well. All right. So I didn't get to go through this problem. Well, we got through this one, essentially. So this problem was motivated by one of the solutions they looked at. They looked at this case of this really unrealistic idea of having heat in the middle of an infinite volume. And they got to something that's a little more realistic. Heat in a semi-infinite volume. This is the half plane. I didn't have a chance to go through this, but I wanted to point out the main difference here. The only difference between these two is this 4, or I guess this 1/4 coefficient turns to the 1/2 coefficient. All right, and intuitively, what this you can think of as being that the temperature And the infinite half plane is going to be larger than the infinite plane in the domain you're talking about because heat no longer can flow in this direction, right? So heat has to go somewhere, it has to now go in the negative z direction, where here it could go in all three directions. This can still go in the x and y direction here. And this is based off the methods of reflection. So if we look at the case, we went through these situations of temperature profiles in infinite rods, and then we looked at an infinite half rod, and using the methods of reflection, we just saw that that was basically just doubling the amount of heat in the system because we can't have heat transferring across that plane. So same idea here. Now this gets more complicated when they talked about this situation. So this is infinite in the y and x direction, and it's finite in the z direction. So our domain goes from 0 to g here. Okay, and so to walk you through their solution here, it's taking the idea of reflections and it's taking it a step further. So if we go back to our class examples with the rod, we looked at a half rod, and if we said we had this initial temperature profile, which we called phi of x, and then we had the Newman boundary condition at 0. The way in which we handle this, if we want to solve this with Green's functions, is that we did what's called an even extension. Okay, so that would be the infinite half space. So that would handle essentially this case. And this would be an even extension in the z direction here, to understand this one. Now this one's more complicated because we have a plane of reflection as z is equal to 0, and now we have another plane of reflection as z is equal to negative g. All right, so the way in which this is done is if we look at x, y, z. So here's our first plane of reflection. All right. But now we have another plane of reflection at the position that's down by a distance g here, actually. But if you look at the literature on, or the math for this, is you have to have an infinite set of reflections to make this work, actually. All right, so we're going to have a plane of reflection at G. We're going to have one at direction G here, and then we're also going to have them G, G. So you have this infinite set of mirrors that is how you handle this problem. Okay. And so looking at if we just look at the z direction, right, because we only have reflection in the z direction, if we said that we had some initial condition for our temperature profile, and we do the even reflection here, that'd be this. And then we have, again, this infinite set of reflections to G, and then, of course, in this direction as well, at negative 2G. Okay, so what we're setting up is, to solve this, we're setting up this infinite set of mirrors for to take this infinite domain into, or say, to take basically this finite domain in Z and turn this into an infinite domain to make this work. Okay. So this is very much hand-waving over the solution, but I want to, I guess, kind of communicate why this was the solution for this finite plane, because we're going to use this quite a bit to try to understand, especially when we're making and looking at heat transfer in overhanging parts when this is going to be useful here. So if you look at then the Green's function for the solution, what we're talking about here is this would be the Green's function if we did not have any reflection at all. If this was just, say, for instance, if we had just a single reflection at the origin, and that would be just for the half plane. All right, but then now we have all these mirrors affecting the situation. So now this is going to be the same thing, except this is going to be z plus 2g squared square root and now we're going to have also a minus 2g as well. And this is going to keep on going on and on for an infinite number of it. Okay, so then the final solution is so again we have an asymmetry in the zeta axis. This is the axis in which the heat source is moving. And then we're going to have an infinite summation of these terms. Okay. So again, keep in mind that these terms are all going to be symmetric in zeta, y, and z. Right. So then I think this is the most instructive plot, I thought, in this paper in terms of what's happening. This is for thick plates, and then they were looking at different responses that you would expect to get when you have heat sources with these thick plates. This is the case of you increase the welding speed. So this is slower speeds. You can see that then the temperature propagates forward more because basically you're moving slower. Heat has more time to propagate forward through the material. You now go faster. It basically shortens where this temperature level set of 200 degrees centigrade proceeds to. So this is very much like what we saw with the one-dimensional case. Now it's just a 3D. If you increase the current, you get this different profile. And then also the other interesting cases they looked at, all right, what happens if you were to change your metal that you're working with? And we wanted to now change the conductivity of this metal. If the conductivity of the metal increases, that means now heat more readily propagates in all directions. So you see now this expansion of these temperature profiles. This moves forward here. So anyway, I thought this was, well, for one, I don't just think this paper is interesting. A lot of people do. This is what's, you go to additive manufacturing conferences and they say, all right, here's the simple solution for temperature. They always call it, like, this is the Rosenthal equation based off of this paper. Right? And this is how we understand basically how temperature propagates in moving heat sources. This paper is really long. It goes through like a lot of scenarios. It even gets into casting, which seems kind of a little far field. But they go through a lot of thick and thin plate solutions. They also look at studying cooling time in metal because this is important for metal microstructure. And then also a lot looking at the idea of heat affected zones, which is, I think, an interesting element that we haven't talked about in this class, but it's going to be important when we get to that in terms of where the metal actually changes in microstructure depending on these different factors. Okay, so that took a lot longer than I thought it was going to. I left no time for discussion. So, so how about then, because we're out of class time. So I think if you wanted to read the paper again, please do so if you have to come up with more questions. But I think on Tuesday morning, we'll just start with maybe the first 10 minutes or so of class. We'll talk about the paper. Any questions you may have, we can walk through those. But unfortunately, we ran out of time today. All right. Any questions quickly, not necessarily whole discussions? Nate?
I just hopefully this is clear. I don't understand why you need an infinite set of mirror planes opposed to just a single.
So I can't say I have a good answer for you on that as well, in terms of why that is from a PDE point of view. Having taken a single PDE class myself, I know that's the answer. Yeah. The simple answer, I guess, one to keep in mind is that if we just had a single mirror, we would not have the Newman boundary condition at G. Right? If we look at the solution. Right? Because we know, trying to think how to best explain this. So this is definitely going to have a Newman boundary condition at Z is equal to 0. Right? This right here, I'd have to think about that. We'd have to take the derivative with respect to Z here. We'd have to take this derivative first and evaluate it at Z is equal to G, or negative G, to see if this is true. I'd have to think about that.
And also, is it true that we would add these reflection planes here as appending terms to the Green solution?
Yes.
I noticed that's what ended up happening when we ran the 1D case.
Yeah.
In classic.
Yep. Yeah, exactly. Right. So that comes from the fact that we're basically changing the reaction to initial conditions, right? So we now need to reflect those initial conditions, even if all those initial conditions are equal to 0. All right. See you on Tuesday. Have a nice weekend.